Hello, everyone, and welcome to Webinar Wednesday. My name is Jeff Jezzard, and I'm with Vector Construction, and I'm thrilled to be your host for this webinar series today. Today, I'm excited to present part 3 of our series, Strength in Repair, Next-Gen Strategies for Concrete Longevity, brought to you by the Concrete Preservation Alliance. In this session, we'll dive into the topic, using fiber-reinforced polymers, FRP, materials to strengthen concrete structures. Thank you for joining us, and let's get started. As this next slide tells us here, FRP is emerging as a widely acceptable and preferred method for strengthening our structures. There has been significant increase in the use of FRP composites on bridges and other unique applications which Travis will introduce shortly. This program is proudly brought to you by the Concrete Preservation Alliance, a global coalition dedicated to advancing best practices in concrete preservation. We extend our sincere thanks to our members and supporters worldwide, whose collaboration and dedication make the Concrete Preservation Alliance and educational events like this possible. A special acknowledgement goes out to the members who have actively contributed content and speakers, helping to educate and raise awareness within the concrete repair industry. Your commitment is invaluable in driving innovation and sustainability in our field. Speaking of sustainability is the heart of what Vector and the Preservation Alliance stand for. One of the most impactful actions we can take in our industry is to preserve and restore existing structures rather than replace them. Restoration not only preserves our architectural heritage, but also significantly reduces environmental impact. On our We've Saved Structures website, we feature an environmental impact calculator. This tool allows us to compare the benefits of rehabilitation versus replacement for concrete structures. By entering the amount of concrete retained, the calculator provides valuable insights, including conservation of natural resources, reduction of solid waste in landfills, water savings, and minimized carbon emissions. We strongly encourage engineers and owners to leverage tools like this to make informed, sustainable decisions for their projects. Together, we can contribute to a greener, more sustainable future. If you registered for this webinar, you're likely familiar with our We Save Structures website at wesavestructures.info. On the site, you'll find recordings and slide decks from many of the incredible presentations we've hosted in the past. These include an array of engaging series focused on topics such as bridge preservation, parking and marine structure preservation, concrete durability, non-destructive testing, and the popular design series. Be sure to explore the site for a wealth of resources designed to support education and innovation in the concrete repair and preservation industry. And finally, one last housekeeping item before we start. We encourage you to take full advantage of the opportunity to ask questions during the webinar. Simply type your question into the chat area and we'll do our best to address them at the end of the presentation. When submitting your questions, please include your name. It's important because we give away a $100 Amazon gift card to the best question. So Travis will go through the questions later and select the best question and provide a $100 gift card to the winner. With that being said, it's time to introduce our presenter. We're lucky to have with us today, Travis Marmon. Travis is a close friend and colleague at Vector Construction, where he has worked very actively in the corrosion mitigation area, PTI, and NACE, and he's very involved in building projects and helping customers. With that being said, Travis, no further ado, good luck and have a great presentation.
Thank you, Jeff. So the topic for this afternoon is fiber reinforced polymers. Over the last couple of years, as design and technology has advanced, we're looking at different options to rehabilitate, to strengthen, and conserve our structures. And one of the ways that we can do that is through FRP composites. For today, the presentation will consist of the concrete preservation process, where we'll take a look at how we determine whether FRP is a viable option for our structure or not. Just briefly go over what kind of codes and guidelines exist, what is FRP and its common uses, also its considerations, the installation process, what that looks like, how we ensure that we have a decent product, by using quality assurance and quality control activities, sustainability, and then case studies. When we look at the concrete preservation process, it starts usually just with a visual inspection, right? We want to take a look at, do we have cracks, spalls, what's going on with that structure? And then we take into account change of use. How old is that structure? What may have happened to it in its life? Was it overloaded at one point? Was there impact damage? And then what do we really want to get out of it? As we look through this chart, the third column from the left, right, we have determine the cause. And a lot of times with carbon fiber, we'll see new uses such as overloading, change of use, code changes. Something's changed over the years, or there was, it's not uncommon where a brand new structure is completed and we see some defects, and carbon fiber can add additional strengthening to strengthen that may not have been installed in the first place. Once we then look to, determine the cause and why we would want to use carbon fiber, then we'll look at life cycle costing, repair versus replace, and then go through the rest of the process of doing the repairs, quality control, and quality assurance. Just to touch on it and know that they exist, ACI, American Concrete Institute, and ICRI, the International Concrete Repair Institute, both provide a good deal of guidance for using FRP systems. In not all cases is FRP going to be the best solution, but if it is something that is being considered, these guidelines are a good place to start. So what is FRP? FRP is a composite strengthening system that usually consists of either carbon or glass, and it's adhered to the surface of the concrete or sometimes installed in channels using an epoxy resin or a paste. Carbon fiber itself is high in stiffness and tensile strength. It doesn't weigh much. They make golf clubs out of it, use it in aerospace, what have you. It's incredibly strong, lightweight. It does have good chemical resistance properties. We do have to watch it with heat because the epoxies don't like high heats, and it's got complementary thermal expansion to the parent concrete. Again, kind of to reiterate, right, it's lightweight, it's flexible in its design. So when we look at designing with fiber reinforced polymers, oftentimes you will treat it in the same way that you'll look at steel. Is that steel acting in a flexural way, in a shear capacity, or in confinement? And in a lot of cases, carbon fiber or glass fiber will mimic those kind of design considerations. The other big advantage is that it's got a low impact profile, right? So a couple layers of fabric of carbon fiber, maybe half of an inch, maybe 20 millimeters or less in multiple wrap situation. So what is FRP? Simply put, one is carbon fiber and one is glass fiber. Carbon fiber, that's the top photo in the darker colored roll. Carbon fiber is, in comparison, much stronger than glass fiber. It also is going to cost a bit more than glass fiber. Glass fiber is often used to confine repairs, to integrate repairs into parent concrete. It is cheaper per square foot or per square meter. However, the installation is identical. We use the same kind of resins. Access would be the same. Nothing really changes in that respect. In the bottom right-hand corner, we have laminate strips, and those can either be adhered to the surface of the concrete, or for smaller laminate strips, they can be installed in channels cut into the concrete. So saw cut a channel and install the laminate with a paste epoxy. As far as applications, we've seen it used on wood, steel, and then of course concrete. It's used for strengthening shear and axial loads. surface mounted, seismic upgrades, barriers. If there is damaged or lost reinforcing, so if you've lost reinforcing due to corrosion, or some wasn't, reinforcing wasn't installed in the original design, or for instance, change of use and loading. We're just seeing much more of that nowadays with people owners repurposing buildings for different uses, and then of course historic structures. So on the top photo there, we have used glass fiber just to confine that pedestal, pipe upgrades, which is a whole different kind of situation where carbon fiber and glass fiber is used. I'm not going to touch on it too much today. And then of course, conventionally, we see beam strengthening in a flexural with shear wraps. Benefits of using FRP, like I said, it's light, it's low profile. We don't need, just adequate scaffolding. We've done a lot of carbon fiber, glass fiber installations over the years using aerial lifts. As you can see in the top photo, that has laminate strips on the bottom of a slab, and then on the bottom photo is a concrete dome where over the years they saw cracking, saw fatigue, and they said, hey, we want to be able to transfer the load from the cap of the dome to the body of the dome, and so they installed glass fiber strips in that case. Pretty fast and easy to install, and you get a lot of strengthening for that effort. Some of its disadvantages, carbon fiber, you do pay a premium for the material itself, but you typically save on your labor costs. One thing that you need to be aware of in this, when using fiber reinforced polymers, is that they can conduct heat and electricity. It's not common. It's just something to be mindful of when you're looking at this as a possible solution. Project-specific considerations. So I come from construction. I'm not an engineer. I'm not a designer. So these are the types of things that I'm really looking at when I'm working with an owner on using FRP as a solution, right? We want to know what the access is. How long will that access be there? Because that has a cost to it. And will that access disrupt the operations of that facility? Will it affect pedestrian or vehicle traffic? Installation time windows. So for instance, on the photo on the right here, they're installing FRP inside of a pipe. That pipe's used for something, for some sort of operation for a factory or a facility. How long will that pipe be shut down? And how long is it going to take to install FRP and cure that FRP so they can put that pipe back into service? If that pipe's out of commission, they're not producing whatever they're producing, so it's a big deal. So those are the things that we're going to work through very early on in the process of evaluating FRP as a solution. Of course, building codes. So when we're using FRP in a residential or a commercial setting or a place or a facility that is habitable, these are things that we're going to have to look into and make sure that if there's fireproofing that needs to be installed, that we account for that in the development of the project. And then of course service temperatures. So epoxies don't like high temperatures. Once you get up to 140 degrees Fahrenheit, 150, the epoxies have a tendency to relax, and that's not good for the FRP product. Active reinforcing steel corrosion. So typically we'll see this like in a bridge construction or a maritime environment where we've got de-icing salts and we know that we have active corrosion going on of our reinforcing. Chlorides are at the level of the reinforcing, so we want to do something to mitigate that. That might be a galvanic anode prior to installing FRP. It is chemically resistant in a lot of different ways, but if you're using in an industrial facility using a different kind of chemical or has a different chemical exposure, we want to make sure that that's accounted for as well. And then of course, fireproofing in commercial residential situations, UV exposure when we've got installations in direct sunlight, and then aesthetic. The nice thing about FRP is that it can be coated with a top coat, typically an acrylic or a urethane that is relatively inexpensive. Considerations in corrosion risk. So for instance, if we're looking at this situation here, on the left, we have a column where we can see active corrosion going on of the reinforcing steel. That middle photo, they've installed a type 2 anode, a galvanic anode to mitigate that corrosion. And then you've got the technician on the right installing the FRP fabric. What we don't want to do is have active corrosion going on, wrap that structural element, and then that corrosion still keeps perpetuating, and we've got spalls and delaminations of the surrounding concrete. It's a big deal, and what happens is that if there's fracturing going on inside of that column because of active corrosion, that carbon fiber isn't participating fully within that structural element. So the project process, so the pre-construction items, right? When we looked at the development process for repair, condition evaluation, and assess the damage. So we want to know what the existing, and these are all going to fall in line with what that FRP designer is going to need to develop a design for the structure, right? We want to know the condition evaluation and assess the damage. Is there widespread chip and patch repairs that need to be done? Are there crack injection activities that need to be performed prior to installing any sort of strengthening? Locate existing reinforcement. If we have the original plans, that's always preferred. That's wonderful. If not, then we may need to do some GPR scanning to locate the spacing and the size of the reinforcement and the depth of it. That's what the bottom photo shows. There is a scan of using a ground penetrating radar to assess an existing concrete structure. I've been on project where we've done both, right? Where we've got the original plans. That's fantastic. We know what the reinforcing is there. Sometimes we'll verify it just to be sure with ground penetrating radar. But a lot of times, especially on an older structure, the plans just simply don't exist anymore. And so we're going to take that information, give that to the engineer of record or the FRP design engineer so that that team can figure out what's required. Structural analysis, determine additional strength requirements. So for instance, if we have a floor and that floor has never been used for, let's say, a warehouse, and they're going to add a lot of additional weight onto that floor, we need to know what kind of weight is going to be installed on, or will that floor be required to handle at that time? So how much strengthening is required? And then project drawings and specifications. Once we have all of those types of variables in place, it sounds like it's a lot. It's just kind of doing your due diligence on the front end of the project. Once we get that in place, a guy like me can put together the budget and the estimate, what that kind of work plan looks like, how long the disruption will be to that facility, what we're going to need to do to install that FRP product. And then after all of that, in the rest of that process will include the FRP design shop drawings. And that's what the construction crews will use to install the FRP. So typical, FRP design drawings, they're typically very simple. They don't need to be too complicated, right? We need to know spacing, offsets, size of the fabric, so we can determine how much fabric or material we're going to need to install. So for instance, on this project here, it's just a typical concrete T-beam. This was a project that I was on where it was a T-beam in a ceiling, and it needed additional strengthening because of snow loads. So we added some additional flexural FRP and then some shear strengthening based off of the additional snow load considerations. On the right is penetration in a floor, and they're adding some additional two-way FRP fabric strengthening. Safety considerations. So the surface prep for FRP is critical, and it does create dust. On smaller projects, we can use an aggressive disc on a grinder. For large projects, it's preferred to use sandblasting. And either of those activities are going to generate a fair amount of concrete dust. So we want to make sure that we have the right kind of containment and make sure that the installers have the proper protective equipment, you know, whether that be a respirator, of course, eye protection, ear hearing protection, and meet all of the different OSHA and standards. Additionally, when we do install the FRP, we're using an epoxies, and epoxies, of course, then require their own set of safety considerations, eye protection, different gloves, Tyvek suits, what have you. So all of this will factor into the price of the installation. So if we're installing something in a hospital, the containment is going to be much more robust than a bridge out in the middle of nowhere, and we're going to have to account for that. Once we've got those kind of variables figured out, we get into the layout of the FRP product. So as you saw in the past in the design, so we wanted to put FRP on a beam. This beam is coated. We want bare concrete. We can't install FRP over any sort of coating, paint, anything else that's there. So grind the existing coating off, open up the pores of the concrete. We want that epoxy resin. We want the ability of that resin to adhere as best we can to that parent concrete, and then we make sure that it's all cleaned up and ready to go. On the right-hand side, you see that there is some epoxy installed on the bare concrete. That's to fill in any sort of bug holes or imperfections. So we don't want any sizable bug holes or imperfections on the concrete, because that is a break between the FRP material and the concrete itself. So we don't want any barriers or any voids there. The project process is fairly straightforward, right? We repair the cracks, usually by epoxy crack injection, concrete spalling, restore the concrete to its original cross section, and then allow for those repairs to cure. Typically, when we know we've got to do repairs and then do FRP right after, we'll use a high performance repair mortar. Again, it's going to cost a bit more, but we're going to save on time. So we want something that sets fast, sets hard, hydrates quicker, so we can get on it and install the FRP quicker. Oftentimes when we don't typically have full access to the FRP repair or installation area, right? We know that we need to strengthen some beams, but we may not in the development process have access to all the beams. Once we have access, we want to confirm the measurements that are there and that they match to what was designed. And if there are any discrepancies, typically not too big of a deal. Get back to the FRP designer and say, hey, there's some differences in measurements here. What do we do? It might involve doing some different detailing of the FRP installation itself, or adding some FRP. And we're typically very conservative in that in the early on process. Then once it's time to do the installation, we grind or sandblast the concrete to get it clean, or cut slots for the near surface mounted laminate strips. One of the issues that we run into is that anytime we encounter a corner and we are wrapping around a corner, we got to make sure that we chamfer and round the corners, typically 3/4 of an inch, 20 millimeters, to ensure that wrap is intimately adhered to all parts of that concrete. And then start installing the FRP. An important thing to note here is we need to make sure that the concrete is cleaned and prepared and has a surface profile, CSP, concrete surface profile of 3. And ICRI, the International Concrete Repair Institute, provides some really good guidance with that. As you see on the right here, we have the ICR chipset. So in the field, you can bring your chipset with you and you can say, look, here we need a CSP 3 or 4. This is the texture of that concrete, and we can compare it to what the technicians have done during their surface prep. Typically, that's achieved by, like I said, a very aggressive disc on a grinder or sandblasting. This holds true with all coatings that go on concrete. Typically, you're going to see a concrete surface profile identified by the manufacturer, and we want to make sure that we achieve that concrete surface profile prior to the installation of either the FRP or a coating. Once we've done that and we've got everything surface prep and it's to the correct profile, we're going to get into the business of installing the FRP itself. We want to set up as close to the installation area as we can, especially if we're dealing with hot temperatures or cold temperatures. It just makes it, to expedite the process, we want to saturate and then get that fabric or that laminate onto the concrete that's going to be protected and give the technicians time to work it over and make sure that it's well adhered. One thing of note on the right-hand photo, insulate between steel and CFRP. Anytime there is essential embedded metals or steel, we have to isolate that from carbon by using glass fiber. Carbon will react to embedded steel or metals, and carbon will deteriorate if over time it goes too long. So it's not that big of a deal. Just need to be aware of it. So if there is anything embedded that needs to remain, it's not a big deal. We just need to make sure that it's isolated. So a typical installation, right, is cut the FRP to size. So FRP typically comes in a 300-foot roll, depending on the type of FRP, but we want to put the largest pieces up as possible. We don't want to splice if we don't have to. If we do overlap, the FRP designer will provide, what that development length or what that overlap length will need to be between two different pieces. But the objective always is try to put the biggest pieces up possible. So on this project, we had flexural strengthening. You can see the fellows on the right, they're putting up a flexural piece, and then there's some stirrups, some wraps around the U-wraps around the bottom of the beam. So put the big pieces up, and then our offcuts will cut those up into the smaller pieces as they're required. Do the surface prep. We'll saturate the surface of the concrete with an epoxy resin. Let it become tacky. Then we'll saturate the fabric itself. You can see the technicians there rolling the fabric and try to put the saturant into the fabric. We do have layup machines that we can use too as well. So you can do this by hand. The machines, we do that. We use those on very, very large projects and saturate that fabric. Once it's fully saturated, then install it into place, work it over by hand, and allow it to cure. Once everything's cured out, then we can install a top coat. So you can see the layup table. The technician on the left is saturating the resin, getting it ready for installation. And then on the right, you can see on the seams, they've detailed the edges of the carbon fiber fabric with a paste epoxy. And that's just to ensure that the edges are tightly adhered to the concrete using a paste epoxy. And then in this case, this must have been a commercial project where fireproofing is required. The team is putting a cementitious-based fireproofing over the top of the carbon fiber. Quality control is critical. So this is part of a structural design. There are different steps to this process that need to be done correctly along the way. And so we have ways of testing and checking and making sure that it's being installed per plan, per design, and that we don't have any problems down the road. So before and after photos are a great place to start. We have QA, QC plans and paperwork, and then of course ICRI and ACI do provide different standards for testing and ensuring that we have a proper installation. So quality control, this is a typical sheet. We want to know what's the ambient temperature. We don't want to install this when it's blazing hot or if it's incredibly cold. Epoxies don't like hot temperatures, and they don't like cold temperatures. So we want to make sure that our ambient temperature, whether if it's inside of a containment or inside of a building or whatever, is correct and not too hot, not too cold, and that steps are being taken to ensure that the layup environment is conducive for the installation of FRP. We don't want high relative humidities or dew points where we're having condensation of water on the concrete. You might see that like in a coastal area or something like that. Surface temperature, and then making sure that it's not wet or damp. We do use a moisture testing meter where we can set it onto the surface of the concrete and it'll tell us the percentage of the moisture on that concrete. Typically we want the moisture below 3% prior to installation of a carbon fiber fabric. And then we want to document the lot and the batch numbers to make sure that if down the road if we've had a bad batch or something was wrong along the way, it's documented. We know that, hey, beams 2 through 5 have this lot number, and then the other beams are that lot number. And then of course our bond pull-off tests. That's one of the bigger one of the more often common ways of ensuring that we've got good bond between the FRP and the parent concrete. And then of course a visual survey to see if there's any bubbles or delaminations along the way. So pull-off test is pretty straightforward. These can be done at random, and then you would have to put another piece of carbon fiber over the top of it. Or a lot of times what we'll do is we'll put an extra piece up that we can use for testing so that we're not putting holes in the stuff into the fabric that is part of the design. We want to make sure that, this will tell us if we've mixed our epoxy correctly, that we've got the correct surface prep done on the concrete itself, and that the installers have laid and installed the fabric as tightly to the concrete as possible. This is one tool that we have to ensure sustainability of our structures into the future. The objective is utilize what we have in our infrastructure and take care of it, maybe repurpose it for other means, and FRP is a technology that we have at our disposal. Seismic retrofitting, where are we seeing it often now? Of course, different parking structures and bridges and those types of structures, but we're also doing a lot with seismic retrofitting, and then the increased use of EV. So EV vehicles are battery powered. Those batteries are heavy, and so now we're looking at parking structures and adding carbon fiber and strengthening those parking structures. to accommodate that. So we're going to jump into some wind farm in a project that was recently done in the Midwest here. So as you can see, these are large structures. The concrete foundation and pedestal take quite a bit of load. In this case, the engineers were able to say, hey, FRP is a good solution for what we're needing for the performance of this pedestal and foundation. So in order to do that, we had to detension the bolts. There's 140 bolts. There's a row on the inside and the outside of the steel shaft that are embedded down into the foundation of a wind tower. They detension all the bolts and then begin the excavation process so they can install the FRP fabric. Prior to the installation, and once they've excavated and exposed the foundation, they saw that there was cracking involved. So simple fix for that was just to inject all the cracks with epoxy, let that set up, and then perform the FRP installation. In this case, the FRP was installed during the winter, so the containment was set up with heating so that we could bring the temperature of the concrete up to an acceptable heat, and then wrap everything, and then of course use that same heat to allow that FRP fabric to cure in place. It was a constant process, and then of course our layup table, we want to lay up as big of pieces as we can around the circumference of that foundation pedestal. So saturated the fabric. Typically we'll use a dowel or a piece of pipe for very, very large pieces that are going to be installed. Get everything saturated, get it into the technician's hands so that technician can work with that fabric and they can get it installed. But you don't see in this photos, there are other technicians behind this installer smoothing down the fabric, getting rid of the bubbles, and making sure that it is as well adhered to the concrete and subsequent wraps as possible. So the final product is pretty simple. Got this one, I think, received 6 layers or 2 or 3 double layers of fabric. They get everything laid up, get everything cured, and then because this is going to be exposed to the soil and UV, at least on the top of the pedestal, they put a UV stable acrylic top coat over the top of the FRP fabric. This is an interesting project. We did this one a number of years ago. Old railway bridge out in the middle of a forest, right next to the river. So the river is high during the spring, summer, and fall months. The best chance to get at this pier was during the winter when the water was at its lowest. So with that in mind, this is located in Minnesota. So they've got plenty of winter. We needed to provide containment for this whole installation. As you can see, significant damage and deterioration of that pedestal over the years. The pads underneath the bearings and then down into the pedestal itself were some fairly good sized cracks that needed to be addressed. And so during the repair process, we needed to get everything contained and get heat put to it. We wanted to bring the temperature of that concrete pedestal or that pier up so that all of our repair materials would be able to cure correctly. As you can see, there was some chip and patch work done on the left, added some additional reinforcing into those repairs, and then conventionally just did an epoxy crack injection on the right-hand side. Once all of that was done and completed, perform the surface preparation, and then wrap this pier in carbon fiber. So rather than building a big encasement or something like that, in this case, perform the chip and patch repairs, fix the cracks with epoxy injection, then wrap and confine it. And then, as you can see, there's some vertical placement of FRP. So that designer that's what they had detailed for this project. Once it was complete, top coated it with a UV stable coating, and then we had to address the pier cap itself. So as you can see, it's in very rough shape, rubbled. What they decided to do on this one, add additional reinforcing, just so like a conventional encasement, and then picture frame it with a steel frame that was acting as a stay-in-place form. So again, you're going to get a lot more confinement out of structural steel. So that's what they decided to use. Installed the reinforcing, doweled it in, epoxied it in, installed the steel frame. And as you can see, it's got the anchors and the Nelson studs to ensure that all of that is participating as one unit. And then you've got the technician on the right casting the overbuild. Once all that was done, they installed an epoxy leveler so that those steel bearing plates and pads were participating fully and had full bearing onto that pier cap pedestal. And there's your before and after. So like I said, you can see on the left, it was in really bad shape. On the right, the rebuild turned out quite well. Another project, similar, but very different mode of deterioration. So this was a bridge that was constructed in 1912. Back then, they didn't have a lot of reinforcing steel, so they didn't just cast mass piers and mass abutments. And in this case, we're seeing some fairly advanced freeze-thaw damage of that concrete. You can see in the top left-hand corner there, and in the photo below it, an incredible amount of cross-sectional loss due to freeze-thaw damage. For the abutment on this pier, we were able to take a lot of the bad concrete off and do an encasement, add dowel in reinforcing, put a mat up, shotcrete it back. You can see right there is a sidewalk there, and the road is right next to it. So we didn't have a lot of room to provide an overbuild, right? But there was enough concrete there that we could remove the bad stuff and just do a conventional encasement. There was no carbon fiber on the abutment. However, and that's in the process of the abutment over the river pier, or over the river abutment there, right? So you've got all the reinforcing steel, shoot it back with shotcrete, and you're done. However, on the piers themselves, we weren't able to overbuild them. One of the piers was right on the roadway, so we had absolutely no room to add additional reinforcing and do an overbuild. In that case, confining those repairs in carbon fiber made the most sense, and that's what you're seeing on the right. So they wrapped the piers in carbon fiber, detailed the edges with a paste epoxy to make sure that those edges don't peel. And once that was completed, they coated the piers with an acrylic paint. Like I said, what you don't see in this photo is that in the background there's actually a road, and that's why they had to wrap them instead of perform an encasement. So long story short, the best way to kind of look at it is in some situations an encasement might make more sense than wrapping, and so we use both methods on this structure. The counterweight restoration in St. Charles Airline Bridge in Chicago. So this is a bascule bridge. Again, historic bridge, old bridge, had a very large concrete counterweight on one end of it so that they could raise the bridge. Over the years, freeze-thaw damage, deteriorated a significant amount of cross-sectional loss of that concrete over time. And what they wanted to do on this one is rebuild it, restore it back to its original cross-section, make sure that they had adequate weight to lift that bascule bridge again. and then they wrapped it in glass fiber and put a top coat over it. So it looks like it's, regular concrete, but in all actuality, it's an overbuild with shotcrete wrapped in glass fiber and then coated with an acrylic paint. And it did win the project of the year. And so if you look on ICRI's website, I think you can find the write-up on this if you're interested. I'm not going to touch on this too much, but I want you to know that FRP is used to strengthen pipe, and it's very common. It's a whole different seminar all on its own to discuss, FRP applications in pipe, how it's used, how it's designed. Like I said, I'm not going to touch on it too much here. The main thing to know is that it does exist. And so if you do have any questions or want, a more well-rounded kind of presentation on something like this, let me know and we can arrange that. It can be used externally, internally, a lot of different ways in which it can be used. So with that, we'll open it up to questions.
Thanks, Travis. That was awesome. Great presentation. Love the project examples. A lot of people see FRP in buildings and slabs, and to see it used on railways and wind is pretty cool, and pipes and things. So I'm going to get to the questions from the audience. I would love to get to all of them. We've got well over 50, so we're going to do as many as we can. And the ones we don't get to, Travis and I will email you back answers and responses. So that'll be done as quickly as we can. But I'll just start firing away some questions here, Trav, if you don't mind.
Yep.
Quite a few asked about water immersion, using FRP in water, or what's a typical process for that?
Yeah, so for installing in water, I'm not as familiar with this, but I do know that FRP is installed around, like a concrete pier or a pile. But in that case, it's a different kind of epoxy, and it is installed back onto itself. So you wouldn't be able to install FRP like on a wall or something that's submerged in water. In piers that, like where the water is low and the water then comes back up in the spring, and the bottom of that pier would be submerged, we would use a different type of coating than what we typically would use. We would use a coating that would accommodate being submerged.
Can you do FRP on steel?
You can do FRP on steel. I personally haven't done it that often. We did do a tank at a pulp and paper mill in a couple years ago, and in that case, we just had to make sure that we wrap that entire tank in glass fiber first, and made sure that none of the carbon fiber was in direct contact with the parent steel. Had a coating on it, had to remove the paint and the coating, then wrap it. Similar to concrete, you can't have a coating or a paint on it prior to installation.
So good question. Since you brought up coatings, are they mandatory, or when do you have to use the coatings with FRP?
So we'll often see is that if coating's going to, so if FRP is going up underneath a drop ceiling or in a parking garage and it doesn't really make a difference aesthetically, if it doesn't require fireproofing or coating, no big deal. If it's exposed to sunlight, we do want to put a UV stable coating over the top of it. If it's exposed to, sea salts or something like that, I'll often see a coating used on it. So depending on its exposure, but a lot of times in buildings, if it doesn't require fireproofing, we don't need a coating.
Excellent. Some good questions around CMU block and brick and different large blocks on old bridges. Is it possible to use FRP on these kind of structures as well?
It is. So we're currently on a project where we have piers constructed out of very, very large stones that are mortared together. In that case, they don't want to overbuild. They don't have the room to overbuild the stone pier, and they don't want it over the footing. So what the designers decided to do on this one was drill and install reinforcing shotcrete an overlay so that we've got a flat surface, and then use additional carbon fiber to strengthen and confine that pier. We've also had situations where on CMU block, we have installed FRP to provide additional strengthening.
Great. I know you've touched on this. There's a lot of questions about corrosion and ASR and existing issues in concrete. And a lot of people think FRP is a miracle Band-Aid, but what could you say about the condition of concrete before you have to install FRP?
Good question. So, I mean, if you have advanced ASR, I mean, FRP has its place. And we really want to do our best in the beginning to get the proper evaluation and testing done and sort out whether FRP is an option. But like if you have advanced ASR, it's not a miracle. Sometimes your better bet is to overbuild it, use conventional steel, rebuild it. I mean, maybe something's too far gone. FRP works really, really well in certain instances, and sometimes it just doesn't make sense.
Do the crews need to go through any specific training? Is there certifications? What makes someone allowed, or what makes someone a good fit to do carbon fiber?
So certain manufacturers require that crews are certified in their product for installation. That's who we work with. It's important for us to have that engineering support from the manufacturer's engineer, that they know their product the best, right? So if we do need to make some changes or some detailing, something, that needs to be changed in the field, they know it best. We can move on quite quickly. They also train you and give you the best practices and certify your crews in the installation of their product. However, there are FRP manufacturers out there that will sell to anybody, and anybody can install it. So it's a good idea, in my opinion, professionally, to vet a installer that has the certification for the product that's going to be installed.
Perfect. I know this is one that tugs at your heart a lot, Trav. It's about cost comparisons. And typically when you're evaluating FRP, what are you looking at? And I know we do dig into this a lot on every project we do, so I'll let you explain that one a bit.
Yeah. So when we're looking at different options and we're comparing different options, right? So FRP, the material is, you're going to pay a premium for the material, but typically your labor is going to be much quicker to install FRP than to do like a larger overbuild, and it might take more time. So we're always kind of balancing different solutions against one another and trying to help inform that owner or that engineer in the best possible way that we can, regarding, the basics of project management, time, scope, and budget. And a lot of that will be based on the different solution and the different design. So it's accounting for safety, it's accounting for access, it's accounting for a lot of things, not just the actual product itself.
Right. Quite a few questions around long-term durability and performance. Can you comment on what you know and what your experience is on how long you've seen it last, or what you know so far about the durability of carbon fiber compared to, say, other repair methods?
It's been around quite some time. And it's, I was looking at a project today where carbon fiber was installed on a bridge 20 years ago, and it looks great. And I know that there was some testing done over the top of that carbon fiber, subsonic testing, and the results were such that, hey, it's in still great shape. The big issue with some of that, or one issue that kind of sticks out to me, is that there's advanced corrosion going on underneath carbon fiber, right? And that carbon fiber is installed over something that has active corrosion going on, and now you've got corrosion that's occurring and you don't know that it's happening. So, but suffice it to say, carbon fiber, if it's taken care of, if it's not damaged in any sort of way, and it's maintained like with coatings and it doesn't have a chance to break down in UV, it'll last typically a very long time.
Yeah, one thing I just like to reiterate, and you've said it a few times, repairs need to be done first. Corrosion needs to be mitigated. Like we're wrapping it, and once you've wrapped it, that structure is what it is. So you have to make sure all those things are done first. If you have bad concrete repairs, a lot of questions revolved around bonding. And I said, well, if you have improper concrete repairs or mush concrete, it's not the answer. Like, you have to get back to a solid substrate. I think you mentioned that earlier, right?
Yep.
Cool. Last question, because we're running out of time here, but there's 50 more here still. But are there limits to how much you can strengthen with carbon fiber?
I'm not an engineer, but yes, I mean, what I've been told is that, I mean, there are limits. Sometimes steel might be a better fit, right?
Mm-hmm.
It might, depending on the situation, a steel beam might be a better fit than adding carbon fiber. That'll just have to be sorted out in the design process.
Perfect. Well, with that being said, I'm kind of running out of time here. I would like to thank you, Travis. That was a great presentation and great questions. Travis's contact information is on the screen there. If you have any more questions, you can send them to him. Like I said earlier, we will go through every one of these questions and respond to it in person, whether it be an email or a phone call. There's a lot of great questions. This was a great information, Trav, and it's spurred a lot of good conversation. So thank you very much. So other than that, if you have not done so, please register for our next session. It's called Exploring Design, Build, and Alternative Project Delivery Methods to Enhance Project Efficiency and Performance. So this session will feature a panel discussion led by industry experts, providing valuable insights and strategies for improving project outcomes. So mark your calendars. You can see there it's February 26th. Of course, it's a Wednesday, being a webinar Wednesday. One more thing, Vector is actually performing a seminar series. So it's across Canada and Midwest and some places in the US. The seminar series will focus on the latest solutions related to the evaluation, restoration, and protection of concrete structures. So you can sign up here. This will also be sent to you again, like I've said before. So these are 4-hour seminars. They usually include a lunch or breakfast, and they 4-hour PDH credits. So great learning things, just the same idea as what we've done here in the last hour, but they're 4 hours and more, definitely more information. So that being said, Travis, thank you, and thanks everyone else. The presentation was awesome. The questions were awesome. And I guess to be said, let's go out there and save some structures. Thank you, everybody. Have a great Wednesday.